Alright, gang, here we go. This is Chem 2, Unit 2. We're going to talk about molecular and ionic compounds. Alright? So, chemical formulas, you've probably had a lot of experience with these. Shouldn't be anything brand new, really, just kind of more of a refresher. So, we've got hydrogen. Alright, hydrogen. Notice that we got this little 2 right here, that 2. That tells us that there's 2 hydrogens. So hydrogen never appears just as a little H. It always comes in pairs of 2, okay? This guy down here, there's water. Notice that we've got a 2. This tells us that there's 2 hydrogens, so here's 1 hydrogen. Here's the other hydrogen, and then this guy right here is an oxygen, right? Hydrogen peroxide, guess how many hydrogens there are? You got it, there's 2 hydrogens and 2 oxygens right here, yep. Okay, so this is how we read chemical formula. So the subscript to the right of the symbol of the element tells us the number of that element that's in that compound. All right, so that's what the little subscript tells us. Now, one thing to be careful of is if you see something that's like, say you got this guy. So we got magnesium phosphate. Okay, you see this. This means that we need 2 of everything that's in this parentheses. So that means this 2 is going to apply to the oxygen and it's going to apply to the phosphorus. So we've got 2 phosphorates and 8 oxygens in that molecule or ionic compound. All right. So molecular compounds are ones that are composed of molecules and are almost always nonmetals only. All right. So remember on the periodic table, the nonmetals were in the top right part. Okay, remember we had the stair step thing. Okay, so they're in the top right. So all the halogens, okay, most of the chalcogens, the noble gases, those were all molecules. All right, there are 7 diatomic molecules. So these are the 7 guys that you need to memorize. All right, so you got to memorize those guys. My high school chem teacher must have been a rock fan. Okay, so she would remember them by Han and the halogens. Okay, so she'd be like, the Han and the halogens, they're coming up next to wrap up the show or something like that. Han and the halogens. All right, it's kind of silly. Some people are, so like another one is you have to think about Dr. Brinkelhoff. Okay, so Brinkelhoff, like this. All right, so that's Dr. Brinkelhoff. All right, or Dr. Brinkelhoff. Okay. Anyway, so either way, you just need to memorize those. So make sure you know anytime those appear. Now, one thing that you need to remember is the diatoms are only diatomic when they appear by themselves. So a hydrogen out in the wild, there's just 2 hydrogen, there's just a hydrogen atom. They never occur as just hydrogen. It always come out as H2. However, these guys can be by themselves when they're included with other things. All right, so if you had like hydrochloric acid, HCl, both of these guys are diatoms, right? Chlorine's a diatom, so is hydrogen. However, because they're together, they can stabilize each other, all right? So they don't have to be diatomic when they are with other things, but when they're by themselves, they always have to be diatomic, all right? We have 2 types of formulas. We got empirical formulas and molecular formulas. Okay, empirical formulas always give the lowest whole number ratio of atoms. Okay, so a whole number ratio, lowest whole number ratios, and the molecular formulas give us the exact number of atoms in each element in a compound. All right, so that's really the molecular formulas tell us exactly how things are. Okay, and the empirical formula is really useful because it's really easy to find with lots of different instrumental or experimental results. So we can find the empirical formula relatively easily, but the molecular formula tells us far more about what's actually going on in our molecule. All right, so we can, anytime we have the molecular formula, we can easily find the empirical formula. We just divide by the lowest whole number ratio. However, if we have the empirical formula, we can't necessarily find the molecular formula unless we have a little bit more information to go on. All right, so just a little practice exercise. We got tetracarbon dioxide, okay? So here we've got, so tetra, if you remember your prefixes from Chem 1, tetra means 4 and di means 2, right? So really this means 4 carbons and 2 oxygens, okay? So we've got 1, 2, 3, 4 carbons and then 1, 2 oxygens. So the molecular formula would be C4O2, right? All right, so that's this guy. All right, and then the empirical formula, we divide these guys by 2, right, because that's the lowest whole number ratio, and becomes C2O, which matches that. So D would be the molecular empirical formula for that substance. All right, empirical formula for decaborane, Alright, so this is the molecular formula. We need to convert it to its lowest whole number ratios, and we can divide each of these by 2, right? So B5H7 would be the empirical formula. And since both those are prime numbers, we can't get it any lower than that. Alright, so we're going to determine the empirical formula. So we've got these two things. We've got N-butane, we've got isobutane. Alright, we want to determine the molecular formula of each, okay? So really we just have to count up the number of carbons. So there's 4 carbons here. So this is C4, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, alright? Now the molecular formula, 1, 2, 3, 4 carbons again, alright? And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Alright, so 4 carbons, 10 hydrogens in both of those. Alright, so the molecular formula for N-butane and isobutane are exactly the same. Alright, now let's determine the empirical formula. So we can divide both of these by 2. We get C2H5 and C2H5. Alright, now notice that if all you had to go on was the empirical molecular formulas, you could not tell that N-butane and isobutane were actually different things. Alright, you couldn't tell if all you had was the answers to A and B. In order to make sure to actually see that there is a difference, you would need that information right there, and that's called the structural formula. Alright, the structural formula right here shows the order in which the atoms are actually attached. Notice how here we've got the carbons attached in like a row, right? 1, 2, 3, 4, a straight chain, whereas here there's like a little branching thing going on. Okay, so the structural formulas show us the order that they're attached. Alright, so that's this guy here. Alright, so there's the molecular formula that we talked about earlier. This is the structural formula. Now the problem with structural formula is that it doesn't really tell us the exact geometrical shape or the three-dimensional shape of our molecule in space. So in order to do that, we have 3 different other options. Well, 3 we're going to talk about. There's other options, but here's the other ones. Alright, so we've got perspective drawings. Alright, so perspective drawings, the way they work is if it's a solid line like you're used to in a structural formula, if it's a solid line, these atoms are in plane. So they're right there on the page. So that carbon and those 2 hydrogens are exactly equal with your screen. Alright, now if there's a dashed line for for this hydrogen, this means that the hydrogen is going back into the page. Alright, so this carbon is right on the page or right on your screen, and that dashed hydrogen is going that way into the page. The hydrogen that has the wedge that's kind of shaded in, that hydrogen is coming out at the page. So this methane molecule is actually like a carbon with 2 hydrogens sticking off of it, and then 2 other hydrogens that are coming in and coming out. And the reason this happens, and we'll talk about this later when we get to Lewis dot structures in molecular geometry, is that all of these bonds are trying to get as far away from each other as they possibly can. Alright, now the next one here is called a ball and stick model. Okay, this guy here is a ball and stick model. Alright, and you can imagine why. There's a bunch of balls and a bunch of sticks. It essentially shows us the same thing, but it's kind of sometimes a little bit easier to kind of tell where things are going and so on and so forth. And then the space filling model, which we've seen several pictures of before already in this slideshow. Alright, so the empirical, so we just got another practice here. Alright, so what are the molecular formulas for ethane? Well, this is C2H6. Empirical formula would be this, all of these divided by 3, so 3, or divided by 2, excuse me, so CH3. Can we infer from this drawing that HCH bond angles are 90 degrees? No, we can't, right? Because this is structural formula. It doesn't show us the 3-dimensional shape. All it does is show us how they're attached. In order to see the 3-dimensional shape, we have to look at a structural drawing, all right, to actually show a perspective drawing, okay? All right, now ions, okay? Whenever we have an atom, remember we talked about before when we talked about isotopes, that in a neutral atom, number of protons and number of electrons are equal to one another, okay? Now, once we start losing or gaining electrons, life gets more complicated, all right? So, anyone that loses electrons forms a cation, right? These are positive. Okay, think about when you're petting a cat, it makes you feel good. Unless you're allergic, then you've got a whole other bag of problems. All right, and then if you gain electrons, then you become more negative, and those are called anions. All right. For the vast majority, things on the left side of the periodic table, form positive ions or cations. Okay, things on the right side of the table form negative ions or anions. All right. So think about it this way. The noble gases, remember, noble gases were special because they don't react to other things. They just don't participate in reactions. Remember, chemical reactions are defined by breaking and forming bonds. Okay, breaking and forming bonds happen between electrons. So the noble gases, essentially, they don't want to share or give away or take new electrons. They are perfectly content, if you will, meaning they're exactly stable where they are. So the noble gases are stable. They don't participate in chemical reactions. So we can assume that the noble gases all want to be, those are this most stable arrangement of electrons. So all of the other elements that are around the noble gases want to either gain or lose electrons to become like their nearest noble gas. So for example, fluorine wants to become, neon is right here next to fluorine. Fluorine wants to become like neon. So in order to do that, it's going to have to move to the right one spot. So it wants to have the same number of electrons as neon does. Okay, so neon 9 has 10 electrons, okay, and fluorine only has 9. So in order to get to be like electron, it has to gain, or be like neon, it has to gain 1 electron, and that's what makes it have a negative charge. See that? So fluorine's going to have a negative charge because it's going to gain 1 electron. On the flip side, sodium's nearest noble gas is also neon, but it's coming at it the opposite direction. It's a long way to get to argon over here. Right? So in order to get to neon, okay, it has to lose 1 electron because sodium is 11. Okay, neon is 10. So in order to get to be like neon, it has to lose 1 electron. So when it loses an electron, it's got 1 more proton than electron, so it has a positive charge. And that kind of continues through, right? So the 1A's form positive 1, 2A's form positive 2, okay? The halogens are -1, the chalcogens are -2, okay? A couple of things to take note of. When you're writing ion charges, make sure to always write the number before the charge. The number before the charge. Notice how they said 2+. It's not a +2 charge. That means something different. That's an oxidation number, and that's going to mean a totally different thing down the road. So when you're writing your charges on your ions, make sure to write the number and then the charge. All right? Another thing I want you to keep track of, okay, is so we'll say aluminum is 3+ here, okay, this guy here almost always forms a 2+, so does this one, and these guys also almost always form 1+, so we get a 3+, 2+, 1+, all right, so make a note of that in your notes. These elements kind of follow that pattern, and for the vast majority, like 90% or more of these 4 elements right here, those follows that pattern, 3, 2, 1, all right. So here's your common cations, all right. So these are, you know, etc., etc. I guess we could talk about the noble gases. The noble gas, or not the noble gases, the transition metals, kind of all the rest of these guys, except for, and even these guys to an extent, all kind of they can gain or they can lose a various number, 1, 2, 3, and sometimes even 4 electrons. All right, and it kind of just depends on what they're bonding with and what else is going on, and so on and so forth. All right. Notice that the only polyatomic cation is this guy, ammonium NH4+. All right, and here's your common anions. All right, notice there's way more polyatomic ions down in this list. All right, so the polyatomic ions, poly meaning many, right, atoms. Okay, so these are things that are ions that are made of many atoms at a time. Okay. And so this is ammonium NH4+, and then this is sulfate SO4 2-. I gave you a handout with a whole list of polyatomic ions that I need you to memorize. All right, so have fun with that. Okay. So let's see. Let's do a little practice problem. No, we're not going to do this. We did it. Okay. So ionic compounds. All right, so molecular compounds, remember those are guys, non-metals connecting to each other. Ionic compounds act a little different. This is where you're going to have a metal and a metalloid bonding with a non-metal. All right, so the classic example is salt, table salt, NaCl. All All right, so you got a metal, that's sodium, and then you got a nonmetal, that's chlorine, and you put them together. And what happens is the sodium, remember the sodium is like, dude, I want to give up this electron because I want to get like my nearest noble gas. And chlorine's one away, right? It wants to gain one electron to become like its nearest noble gas. So what happens is sodium's like, dude, I'll give you this. And then chlorine's like, yeah, give me that. Yeah. And so then they kind of do their thing. So sodium loses his electron, right? So he kicks it off down here, and chlorine's going to take his electron and going to gain it, okay? So now because sodium has 11 protons and 10 electrons, it gets a positive charge. And now chlorine has 17 protons and 18 electrons, so it gets a negative charge. So the positive part of the sodium and the chlorine part, or the negative part of the chlorine, they get charged. And then they're going to get attracted to each other, kind of like magnets. You got a positive and a negative magnets, and they're going to get attracted to each other. All right. Last little bit here, writing formulas. Okay. So you've got these ions, and we need to be able to write formulas as they connect to each other. Okay. So you got magnesium 2+ and nitrogen 3-. Now, the easy way to do these is just to flip them. All right. We call them the crisscross method. So the 2+ here becomes the number 2 over here. See how it became the number 2, and the 3 over here becomes the 3 over here. And so Mg3N2 is how these two would combine. All right. So crisscross method. The only problem you need to make sure is that if your subscripts are not in the lowest whole number ratio, divide them by the greatest common factor. And we'll see an example of that coming on. All right. So let's write out the empirical and compound formulas formed by these guys here. So this becomes, so the 3 is going to come down here, and the 1 from that is going to become down here. So it's going to become AlCl3. All right. Crisscross again, so this becomes Al2O3. All right, and then this last one we got magnesium and nitrate. All right, so this becomes Mg and then NO3, but we need 2 of them, so we'll put parentheses because we don't just need 2 sets of the 3 oxygens, we need 2 sets of all of this. Okay, so this too. So ask yourself, how many of each of these 2 things do I have? Well, I've got 2 nitrogens and 6 oxygens in here. All right. That's them working through it. You can read through that on your own. Cool? All right, let's do one of these real quick, and then we'll call it a day. All right? Or 2. Let's do this one here. All right? So we got zinc and sulfate. All right? So we'll crisscross. So this becomes zinc 2, sulfate 2. But this is a problem. Remember, our last rule back was that if they're not in the lowest common ratio, then we're going to get rid of them. So these 2's are going to go away. And really, if we wrote this out, so it was a little neater, it becomes zinc sulfate. All right? Cool. So that's it for right now. Next video, we'll be talking about nomenclature. We're going to talk about ionic compounds, acids, and binary molecular compounds. And then we're going to talk about some simple organic compounds, alkanes and alcohols. Should be a lot of fun. All right. Check you later.